Hi everyone, welcome to the latest episode of Quantum Mechanics for Everyone video series. If you have not watched my previous episodes yet, I encourage you to go through all of my previous videos. So all the prerequisite knowledge is there in my previous videos. If you have not watched it, let me put all the links of my previous video. You can find out all the video clips and the descriptions and all the links on the description section, so I want you to go through all of those videos in advance, right? Today's video is another fascinating concept that I'm going to walk you through, another fundamental yet a very powerful concept that you must learn prior to those deep concepts like tunneling and free particles, and even when you reach the ladder operators. And prior to all of those concepts, guys, it's better or it's essential to walk through this concept, which is particle in a box. Or simply we can say this is a 1D potential wall, so 1D infinite potential wall. Why do I take this as 1D infinite potential wall? What I'm going to do is, this is an imaginary situation, guys. It's um, you are impossible to find, you are unable to find, it's impossible to find a particle or a region where the potential is infinitely large. But for an instant, we are going to take that potential inside of this. So this is a well, in the sense, let us take it as a well, guys. And here the potential is 0 in this section. So in this region, the potential is 0. Just imagine a region where potential is 0. This is imaginary, right? But a very important fundamental concept is going to be derived, right? And here potential will be infinitely large outside of the box. And even here, now, right, if I start with x equals 0 here, this is x equals 0 region, and this is the region where x is less than 0. And here there's a region, or at this point, that's x equals a. And even here the potential, these guys are infinitely large, right? So now it's pretty obvious, even if you view it from the particle perspective or classical perspective, it's pretty obvious that particle can't ever reach this region or that region because of this infinitely large potential. That's the first important thing to be noticed, right? Now we already know that this is a quantum particle. We're no longer talking about some huge particles. Those are quantum particles, guys. In the sense, those are fundamentally quite small particles. And we already know, unless it is observed, the particle behaves as a wave, or I would rather say, in fact, you can use a wave function. So that is something called a wave function, right? Particle itself acts as a wave function, right? So now there's a wave function here, right? And if you have not gone through my previous video, you must go through my previous video, because most of those concepts are there. Most of the useful concepts are there in my previous video, right? So in that video, I mentioned that here, when the potential is 0, right, we can separate the wave function, and we can write the time variant of the wave function separately, and the next part of the wave function, it depends on the x. And even I told you that you can straight away use the time independent Schrödinger's equation, which is Ti independent S E Schrödinger's equation, right? And you can remember what the time independent Schrödinger's equation is, as this is as the potential doesn't depend on the time. It's not a a function which depends on the time, you can straight away use this time independent Schrödinger version for e is equal to E5, right? And in fact, this is the H operator you already know that I told you. And this is the operator that, which is corresponding to the energy, right? Which is corresponding to the energy. And moreover, these are eigenvectors, and this is an eigenvector or eigen function of the, when the phi is an eigenfunction of H, right? So we can get the energy, right? So now you must be already familiar with this stuff, because if you have gone through my previous video, I'm pretty sure you must be already familiar with that. And even if I go one step, if I dive one step deeper, now I will end up with this final equation, which is minus h bar over 2m, right, d squared. I'm not going to use partial derivatives this time, because we already know the time is no longer, time is not going to interfere. You can straight away use this equation. Therefore, d squared 5 over dx squared plus v5, and we already know phi is a function of x, right? In fact, this is phi x is what we're talking about. But it's for simplicity, guys, I just leave it as phi here, because it's much easier to keep it as phi here, right? Now the catch is, we already know that particle can't reach these two ends. Particle has to remain inside this this region. So I can clearly say that if you are talking about this well, you can straight away take v as 0, guys. So v is equal to 0, because in this region it's a free, not a free particle, but it is a particle which is contained in this region. Therefore v would be 0. So I can now straight away write that E5 is equal to minus h bar over 2m d squared pi over dx squared, and that's all. Here now this part is 0, right? Now I want to find what exactly the wave function look like. That's what my next objective is, right? Let's give it a try. So now, guys, let me start it over here, right? Now I can clearly see that my second derivative is d squared phi over dx squared is what my second derivative is equal to here. When I take all of those things to the other side, I will end up with 2m e over h bar, and don't forget to move this minus term 2 to other side. So now this is what it finally looks like, right? And here that is in fact phi, right? Okay, now I want to find out the relevant phi here. Of course, yeah, you can take exponentials, right? Even exponentials will perfectly work, or else you can use sine cos, right? We already know to describe wave function, you can either take exponentials or you can rely on exponentials. It's up to you, right? But here, for simplicity, guys, I'm going to take trigonometric relationships, cos, sine, right? What if I take sine? Let me take, I assume that my phi x would be equal to a sine kx, right? I don't know what the kx is, but if I take the first derivative of this one, let me take the derivative twice, right? So when I take the first derivative of this one, d over dx, and it would definitely look like a k here, cos kx. Take the derivative again, once again, d squared pi over dx squared. Right, now interestingly, we will end up with minus a k squared, right, and sine kx, right? Now we can clearly see that a sine kx is equivalent to phi, which is exactly the wave function because I have already taken as phi x. So now it will leave behind this relationship. What is it? D squared phi over dx squared is equal to minus k squared phi. Wow, that's a super cool relationship. Moreover, you can say that k squared is equal to this section, which is it 2me over h bar squared. Right. Put it aside. What if you take, you can work it out, guys. You are smart enough to work it out. What if you take phi as b cos kx, still the same k? I'm pretty sure you will end up with the same sort of solution, right? So then now we have two solutions, guys. I'm not going to simplify this. You are smart enough to do that, guys, right? And you'll end up with the same solution. So I can clearly see that phi x, a sine kx is a good solution for phi x. Then apart from that, we have another solution. What is it? B cos kx is also a solution. So when you have linear solutions like that, you have to write as always, that's a linear relationship here. So you can straight away write that here phi x is equal to what? A sine kx plus b cos kx. Right. Here, I can straight away, so I want to pull out something from this and yeah, I want to check what it is. I have so many problems to deal with here, guys, because I don't know what exactly the A is. I have no idea what the B is, and literally I don't know anything about the wave function yet. I mean, halfway done. We know what exactly the wave function would look like, could look like, but we don't know what exactly this is the wave function is, and we will find what the A and B is. Right now, mathematically, guys, there are some now. Right, so now here you can clearly see that already the particle would never appear here, guys, because there's already potentially infinitely large. Therefore, there's no way that the particle could reach this end. On the other side, the particle can't ever reach this end too. The particle somehow can't ever reach this side or the other side. So now just take a note, guys, if you want. This section is essential, it's needed, right? So now what I'm going to do is I need some more space to work it out, right? Now, yeah, as we already know that phi x, or when the phi here x is equal to 0, right? The phi 0 must be 0 because particle can't ever reach this end, guys, because of that infinitely large potential. So now I can find out that when I substitute that value to my to the wave function that I have already found out, that would be phi 0 is equal to 0 is equal to a sine 0 because x is 0 plus b cos 0. We already know that sine 0 is 0 and the cos 0 is 1. So now I will end up with b is equal to 0. Right. I have already figured out what the b is. So now I'm pretty sure that the wave function would finally look like phi x is equal to a sine. Now there's no b part anymore. So it would look like a sine kx. Are we done? Not yet. Furthermore, now I have to use this space, so let me continue it over here. So we apart from that, we already know that phi a must also be 0 because particle can't ever reach this end because of this higher or the infinite large potential in this section. So that's also 0 is equal to, if I substitute that value over here, which is a, I will end up with this a sine k a. Awesome. Now, even if you move this a to other side, put the wave function aside prior to the wave function, guys, before uh, finding out or before exploring what exactly the wave function looks like, we are going to explore something quite useful. Let me uh, let me show you what that useful relationship is in advance, and then I promise you that I'm going to walk you through what the wave function is, and I want to show you what exactly the wave function look like, right? But here now, even if you move this a to other side, I will finally end up with sine ka is equal to 0. Sine ka is equal to 0. Now what? Guys, it's pretty sure now the ka should be a product of pi. Then only, because we already know that sine value will be 0 only when sine value is 0 only when the angle is equal to a whole number product of pi, right? So now guys, ka is equal to n phi, right? And we already know what the k is, but I'm more than happy to have k squared, because I'm not happy with the k because the roots will involve. So we have to just we have to be very careful, because we have to deal with clean mathematics here. So what I'm going to do is I'm going to take the square of them. Let me take k squared, a squared. Here it will be n squared, pi squared. Furthermore, we already know k squared is 2me over h bar squared. So now, 2me a squared over h bar squared is equal to n squared pi squared, right? Then finally, I will end up with something majestic, something inspiring, and something fascinating. So let me show you what this fascinating final relationship is, which is, please welcome, E is equal n squared pi squared h bar squared over 2m a squared. 2m a squared, right? Very interesting. Now, if you are smart enough, now you should be able to understand that E can't ever be 0. E can't ever be 0. Why? If the A becomes 0, it turns out that wave function itself is 0, guys. Right? If now imagine if the k is 0, because when the A, because we already know that, right? E is a part of this k squared. Then k squared is equal to me over h bar squared. In the sense, as the E reaches 0, or if E is 0, it will turn out that k is 0, and of course it will turn out that entire wave function becomes 0. Then wave function doesn't exist. There are two mathematical problems with this. If the wave function is 0, the first problem is you don't have a particle here, guys. Because we already know that wave function squared, the square of this one represents the probability density of the particle. In the sense, you should be able to find the particle somewhere, guys. If it is 0, you can't find the particle nowhere. So then this contradicts everything that we have been discussing so far. And the second problem is even more dangerous. Even more dangerous, guys. If the k is 0, the energy, or put the energy, sorry, energy is 0, the momentum of the particle would be 0. The momentum of the particle would be 0. In fact, the momentum is certain. The momentum is certain, guys. That's a problem, because we already know that the momentum uncertainty, delta p, and the position uncertainty is equal or greater than h bar over 2. Whose relationship is this? I haven't discussed this yet, but this is called the uncertainty principle. You can't ever violate the uncertainty principle in quantum mechanics or in fact in physics, right? So therefore, this is unacceptable, guys. That's an unacceptable condition. Then you can clearly see that energy of a particle would never be zero under this circumstance, guys. So when the n equals 1, you get E equals 1, right? So here, let me erase this part. I want to show you something very useful and very important, right? So now I can see that E1 would be when n equals to 1. That is exactly the first energy level is, right? So here pi squared h bar squared over 2 ma squared, right? And moreover, when n is equal to 2, E2 is equal to pi squared, or here 4 actually, because 2 squared is 4, pi squared h bar squared over 2 ma squared. What about n equals 3? Right, we can go ahead like that. E3 is 9 pi squared h bar squared over 2 ma squared. Right, the catch is, I can clearly see that quantization of energy, guys. You can't find the energy in between these two, right? In between these two. So those energy levels are, and these are exactly the outcomes, or simply you can say these are the eigenstates or eigenvalues, eigenvalues of the energy, right? So you can find something in between, right? And that'll be another part of this video, because this is very important, guys. So those who dive deeper into quantum mechanics must understand these core relationships. Don't ever try to remember them, right? Don't just rely on these equations. It's pretty hard for you to understand, guys. The nature or the beauty of quantum mechanics you can't ever see if you just rely on this equation. Try to understand these things, and then only you can feel the quantum mechanics intuitively. That's my responsibility here, right? And moreover, here now I can clearly see there's one more thing, guys. What about A here? So I haven't proved the A yet, because I have to do it now, right away. Now I'm going to do that, guys. Now that will be the last part of this section, and then in my second video I'm going to show you some more important relationships related to this 1D infinite potential wall, right? So let me go ahead and do it for you guys. So this next important thing is the A, right? We already know a wave function is something like this. Now A sine kx. But the problem is what the A is. Without knowing A, this will be incomplete. This will be incomplete, guys. So now I have to do something about it. So that's what I'm going to do now. So what if I take, this is important. Now we already know that pi x squared and the square root of that represents the probability density at x, a squared sine squared kx. And we already know that the particle could be found in between this, in the sense 0 to a, nowhere else. So then here 0 to a, if you take the integration or the area, that must be equal to 1. The total probability of finding the particle in between these walls. So in fact I can now say that 0 to a, if I substitute over here, a squared sine squared kx is equal to 1, right? It's 1. Put the 1 aside for a while. I have to first of all deal with this one, then I'll come back to this, right? So what if I erase this part? I need to find some more space to wrap it up. Right, now I'm pretty sure you are good at math. So then here guys, we already know that sine squared kx can be written as, or can be written in terms of cos 2x, because we already know that the cos 2x is equal to, sorry, to cos 2kx, my bad, cos 2kx would be equal to 1 minus 2 sine squared kx. So now I can use this relationship. This is a very useful trigonometric relationship. So I can use this. So I'm going to rearrange this equation. So I'll end up with what? Let me start it over here. Now I'll end up with when I rearrange the equation, a sine squared kx would be equal to here 1 minus cos 2x 2kx over 2. Interesting. What if I substitute over here now? Yeah. So now it's a clear 0 to a. It's a clear cost relationship here I can end up with. So that's even here 1 minus or half minus here cos squared, sorry, cos 2kx over here 2, right? My dx is waiting out here. Right, now I can take the integration of this one. It's pretty obvious now. I will end up with here x over 2. If I take the integration of first one, it will be x over 2, where this one goes to 0 to a, minus here cos 2x is when I integrate the cos 2x, I will end up with sine kx, sorry, sine 2kx, and here the 2k comes and joins here, and that is now even 2 times 4, 2 times 2 is, I'm going to straight away write it guys, it will be 4 here, 4k, right? And here 0 to a. And previously we discussed guys that even if you substitute here a sine 2ka or sine 0, the both of them will be 0, because we discussed it previously guys. Because in the previous wave function I told you that sine ka, because when you substitute x is equal to a or x is equal to 0, boundary conditions, that's 0, then this will be eliminated straight away. This will be eliminated straight away. So now I can straight away mention that this is the one which is going to retain at the end of the day. So now I can write down that this is a over 2 minus 0. So that's a over 2 at the end of the day. So now I can substitute over here, because I have just found out what the derivation is. But there's a catch here. A squared is waiting out there. I forgot to mention it. Right, when I get the derivative here, the a squared is here waiting out there. Right? So I ended up with, because I deliberately avoided a squared, so which is waiting out there. Right? So now I will end up with what? Right? I know what the a is now. So a sine kx is the equation, is squared sine k squared kx and a squared, and anyways now a squared, because I have found what the derivative is, a squared times a over 2, right, is equal to 1. So a would be now is equal to 2 over a squared, right? It's about to wrap up this relationship guys. It's over now, because I can say my phi x will be now what, which is a sine kx, right? And even now phi x would be here a is 2 over a square root, and I have previously found that here sine, and we already know what the k is. You can substitute, go ahead and substitute what the k is, right? You will end up with the right value, the right function, right? So then, so that is what the ultimate wave function looks like. And in my second video, I'm going to walk you through something more sensitive, guys, and keep in touch. The second part is fascinating, and second part is quite useful. The characteristics and the usefulness of this, and most of the other interpretations will be, and some other useful. In this context, we have to learn some other stuff which could really help you to understand tunneling, free particles, ladder operators, and even some other fascinating concepts, right? So then keep in touch. See you in the next video, guys. Bye bye.